Hello, I am Abhiruchi and I'll be talking about support vector machines. So, what exactly are support vector machines and why do we need them? So, we'll have to learn machine learning algorithms beforehand. As you may know, machine learning is a type of artificial intelligence in which we use the machine. Actually, the machine learns from the data that we have, and they can teach themselves to grow and change when exposed to new data. So basically, the machine learns from the data that you've provided, the training data, and then you may use it on the test data to generate outputs as you need. So there are various types of machine learning algorithms. They can be classified as supervised, unsupervised, or reinforcement learning algorithms. So basically, in supervised learning algorithms, they consist of a target variable which is to be predicted from the given set of predictors. So basically, we have our training data and we want to find out a class or a target variable on the test data that we provide. In unsupervised learning algorithms, we usually do clustering. So we have various groups and then we divide them into various kinds of data, and then we divide into groups so that most of the members in a single group are similar. And in reinforcement learning, we expose the machine where it trains itself continually using trial and error methods. So basically, it just improves from the time on from when we have started. So that is the basic introduction that we need. Now we'll turn on to our main topic, which is support vector machines. So basically, support vector machines are machine learning algorithms based on the Vapnik-Chervonenkis theory. Here we have support vectors, and then with the help of hyperplane we divide those support vectors into different type of classes. So let's take an example. So here, as you can see, the red dots and the green dots are the support vectors that we have in this type of data, and we want to divide them using an hyperplane so that we can classify the test data accordingly with the help of these support vectors. So as I've written there, support vectors are the coordinates of individual observations. So the green dots and the red dots are support vectors, and the support vector machine is an algorithm which segregates these two classes, that is the support vectors, using a hyperplane. So the hyperplane is the dotted line that divides it. So there are two types of SVM, which is support vector machine. So the first kind is linear SVM. So as you may see in the left square, the data there can be divided by a curved line, but the same data, when you apply a function phi on that data, it may convert into to the kind of support vectors that can be divided using a straight line. So you may divide the convert the data into a kind of data that can be divided by a linear SVM, or the second type is non-linear SVM. So here, as the data is scattered into clusters, and even though you may convert them into linear SVM, but you will have to use various functions phi, because one function phi would not divide them all. So we tend to use a kernel algorithm for dividing this kind of data. So now we'll actually see how SVM works. So the first and the foremost thing that we have to do is we have to identify the right hyperplane. So as you can see in this scenario, we have stars, blue colored stars and red colored dots. We will be using the same example now on. So we have stars and dots here, and we need to identify the correct hyperplane, which is very important because that hyperplane is what decides where the test data that you have to classify will go. So here we have three sample hyperplanes, which are A, B, C, and as you can correctly see that B hyperplane segregates the stars and the dots properly into two classes. So in this scenario, for the first step, we will select hyperplane B as the correct hyperplane. Now that we have identified B, now we can also deduce that there may exist various parallel lines to B that may be the hyperplane that divides it. So assuming that the parallel lines are now A and B and C, which can divide these support vectors. Now, which one will be the correct hyperplane among these? So the data says that the margin, which is the distance from the nearest data point or the nearest support vector, that should be maximized. So the hyperplane should be far from both of, or how many support vectors that you have. So as you can correctly identify, the support vectors, the hyperplane C is far from the stars and also from the dots. So C would be the correct hyperplane. Now this is because as you have a higher margin, the robustness of your algorithm increases, because say when you have a test data which is lying on the hyperplane, the algorithm will get confused on whether to classify it as a star or a red dot in this case. But if you have a hyperplane which is equally far from both of the support vectors, the algorithm will be able to classify it correctly as a star or a dot. Now in the third scenario, we have stars and dots again here, but now we have two sample hyperplanes which are A and B both. So which of them would be correct? Because A divides them correctly into two separate support vectors, but B is equidistant from them both. So either of them can be, but the correct hyperplane would be A, because A segregates them into two different hyperplanes, and that was our first rule, that it should correctly separate out both of the classes. So B won't be, even though it is equally away from both of the classes. So A will be our correct hyperplane. Now in this scenario, we can see that in the stars and the red dots we have an outlier. So outlier is a class or instance of data that is not present in the cluster that it is supposed to be. It is somewhere else. So outliers are basically the unexpected kind of data which are not according to the normal expected form. So SVM is has one advantage, that it is robust to outliers, saying that if there are many outliers present, it will consider them, but if there is just a very negligible number of outliers, it will ignore them as abnormal, and then find a hyperplane that has maximum margin from the normal sample data. So line between the star and the red dots will be the correct hyperplane over here, ignoring the outlier. Now yes, now we have seen all about linear hyperplanes. So in this scenario, you can see that the stars are circling the dots over here. So how do we separate these two classes using a straight line? We can't. So that's why kernel methods functions come in handy. So these kernel methods divide the low dimensional input space into a higher dimensional input space. That is, say if you have a 1D figure, sorry, a 2D figure like it is here, based on x and y axis, it transfers it into a 3-dimensional figure, that is a higher dimensional space. So let's see in the example. Yeah, now the 2-dimensional circular figure is transformed into a 3-dimensional figure in the first left hand side figure. So as you can see, we use the formula z is equal to x square plus y square. So the points when now substituted are looking like these in the left hand side figure. So the left hand side figure can be easily separated out by a single line. But as you can see, the function that we have, z is equal to x square plus y square, it is the function of a circle. So after converting the hyperplane that we have in the left side figure, it transfers into a circle, like we can see in the right hand figure. It's actually an ellipse. So the ellipse will be the correct hyperplane that divides the two classes over here. So this is an example of a nonlinear SVM. So we have seen all about linear and nonlinear SVMs and how to identify them correctly and what they are and what would be the scenarios in which you have to identify them. So now we'll see just an implementation of SVM on a sample data set. So I'm using R Studio for that, and I have a code written in R, and I'll explain the code as I'll run this. So basically we need a library for running the machine learning algorithms. So the library E1071 is useful for all the machine learning algorithms. So we'll just import that library. So I'm running this and the library is imported. Now we have a sample data set which is called as iris. So we are familiar with iris from Becca. So as you can see, the iris data set is plotted over here according to their features, which are sepal length, sepal width, petal length, petal width, and the classes are species. So this is the iris data set that we have here, and in this data set we have 150 records, and the classes, the species of the flowers that we have are, the first one is Setosa, second one is versicolor, and the third one is Virginica. So this is what we have, a 150 record data set with three kind of species divided on four kinds of features, as you can see in the plot. The four features, three species, and 150 records. So now we have plotted the whole iris data set, but as you know, in SVM we have to segregate them into a hyperplane. So we'll just select two of the features, that is sepal length and sepal width, and plot the iris data set according to those two features, and the features will be divided by species. So yes, I'll plot that, and as you can see, the classes are color coded. So different classes have different colors, like you can see the black color, red colored, and green color. But you can see that the data here is not completely separated out. The black ones are separated out, but the green and red ones are too inbuilt to be divided by a hyperplane. So we'll use the next two features, that is petal length and petal width, and divide the data according to the species in hope that we can segregate them properly. So here is the data that we have plotted. So yeah, this is segregated properly. As you can see, the black ones are separated out into one cluster, and then we have the red ones with few outliers and the green ones. So as you can see, this is more easy to be distinguished by a hyperplane. So now that we have correctly identified that the petal length and the petal width would classify the data properly. So now that we have 150 records of the iris data set, we'll select 100 random records of that data set into our S variable. So S variable would have 100 samples from the 150 data set. Now this is because we need to train the data, train the algorithm first, and then we need to apply the test data. So what we'll do here is that we'll use 100 samples to for as a training set, and the remaining 50 samples as the test set. So here we have given the code that 100 samples are the training set, and the minus s, that is the remaining samples, that is 150 minus 100, which is equal to 50, would be the test set. So now we have a sample set and a training and test set. So we'll segregate that 150 samples according to petal length and petal width, because we have established that petal length and petal width classify the data properly. So here we are executing the code of getting samples according to petal length, petal width, and training and test data. So now we actually come to the SVM model part. So this is an inbuilt function in the library which classifies the data. Now we have to classify the data according to the species. So we specify it over here as we want the output as Virginica, versicolor, or Setosa. So we'll give that over here as the species according to which we want to specify, and the data that we want to train it on is iris train, and the kernel that we want to use is linear, because as you can see, a line can simply divide this data, and the cost is the cost function that we have to use, and as the kernel that we are using is the linear SVM, so we don't need to have any kind of scale, so scale is equal to false. So now we are applying the SVM model on the data, training data, and now to print that. So here we have 50 test data, right? So the number of support vectors that we have is 48, right? and we'll plot that SVM model so the output is more feasible. So yes, as you can see over here, it divides the data into the 50 test data into 3 classes. So we have Setosa in the green region, versicolor in the red region with white region with the red crosses, and virginica with the pink region and green crosses and circles. So the SVM is working right now. So as this cost function has not been explained, we'll do cross validation. So basically this is the tune function is like correcting, cross-checking the SVM model whether it is working right or not. So the tune function has a variable called ranges, and in which we can find the cost that is the most efficient for that function. So we have given a range of cost over here, as you can see, from 0.001 to 100. So let's just cross-check that, and as you can see over here, the best parameter of cost is 0.1. Okay, so that is why we are using the cost as 0.1 over here in the SVM model. So yeah, that's done, and we have taken the summary, right? Yeah, so now we need to plot the iris test data, because now we have trained the data as we want according to the SVM model. We want to test the data, the remaining data. So we'll predict the species of the test data that we have taken, the 50 samples. So we'll use the predict function for that, and we'll pass the SVM fit model. So here's the SVM fit, that is the SVM model algorithm, and the test data of 50 samples, and the type is equal to class, that is the type is equal to species. So we'll predict that, and we'll plot the output, and we'll also plot a table. So here you can see the Setosa samples are around 19, and versicolor are 16 actually, and virginica is 14. So as you can see in the table over here, as I am highlighting, the Setosa samples are identified correctly, all of them, but the versicolor sample is identified wrongly. One of them is identified wrongly as virginica, and same goes for virginica, where one is identified wrongly as versicolor. So the table shows that, and now we'll take the mean. So the accuracy is shown over here of the code that we run. So the accuracy is 0.96. So that is the SVM model that was created here according to the random 100 samples. The accuracy that we have is 96%. So there's that. And now the code here, it selects random 100 samples and 50 samples as training and test data respectively. So the accuracy that we have is going to change according to the samples that we take. So if we implement this code again, the accuracy may change. So let's try doing that. We'll implement the code again. So here you can see the accuracy is now 94%. If we do that again, it may increase or decrease depending. It says the same 94%. So there's that, and we're done with the implementation. The code is over here, and this is the output that we have, and this is the classification that has been done, and this is the accuracy 0.94, that is 94%. Now returning back to our PPT, now we'll just see the pros and cons associated with SVM, because there have to be some advantages and disadvantages. So the advantages of SVM is that it works really well with clear margin of separation. Say you have a data which has been separated or segregated very properly, it will give you very accurate results. As you could see in the implementation part, we chose the features accordingly because we wanted a clear margin. Now it is effective in high dimensional spaces. We used a two-dimensional model over there where we used two features of petal width and petal length. So it worked effectively, because if you just use one-dimensional space, it won't have a lot of training data to learn from. It is also effective in cases where number of dimensions is greater than the number of samples. This is because it makes the learning more efficient, because the number of samples when done in a lot of dimensions is more efficient. And another advantage is that it uses a subset of training points in the decision function, and so it is also memory efficient. So Yeah, this is just the training points, and decision function is the support vectors or the training set that we had. And this is because we just don't need a separate training data to for the algorithm to learn from, so that makes it memory efficient. Now we just see the disadvantages. So the first one is it doesn't perform well when we have large data set. Yes, this is because when you have a smaller data set, it has less to learn from, and it does that quickly. But when there's a large data set, it has to learn more, and it has to remember more dimensions, more features, and more amount of data, which takes a lot of time and reduces performance. The second disadvantage is that it doesn't perform very well when the data set has more noise, that is more outliers. So the SVM, as we saw earlier, tends to ignore outliers. So when we have a lot of outliers, it will actually ignore a lot of important data, and that would lead to, in reduced or lower performance. And the last disadvantage is that SVM doesn't directly provide probability estimates. These are calculated using an expensive fivefold cross validation. So yeah, as we did the cross validation using the tune function, so the SVM doesn't directly provide a probability, so we had to use the predict data set and everything. So we did the whole implementation in R, but if you want to do it in Python, you can use the scikit-learn library. I'm more familiar with R, so I used R. So yeah, that's done, and thank you very much.
हुआ क्या?